So let's first cover aldehydes. Aldehydes are a functional family that have a carbonyl group, which is this carbon double bonded to oxygen group, at the very end of the carbon chain. Usually, we don't draw hydrogens in organic compounds, so this would really just look like this. However, it does look kind of weird hanging off the end, so you will usually just see it with a hydrogen next to the carbonyl group. Next, we look at dialdehydes. Sometimes we can have two carbonyl groups in a compound, and those would be at the end of the chain, and that would be a dialdehyde. With ketones, they are very similar to aldehydes. However, the carbonyl group is not at the end of a chain, so notice there is no hydrogen here. Rather, it's another carbon. Note that here, the carbonyl group was on carbon 1, and with a ketone, it has to be on carbon 2 or more. It cannot start at the first carbon. Then, just like dialdehydes, we can have diketones, where we have two or more carbonyl groups in the middle of our chain. We can also have cyclic ketones, where we have cyclic compounds like cycloalkanes with a carbonyl group coming out of them. Now with ketenes, we have a carbonyl group directly double bonded to its next door carbon. This does not leave room for any alkyl chain coming out of the other side of the carbon. So with ketenes, the carbonyl is always at the end of the chain. Let's take a look at the ending of our main chain. Each of these groups have a different ending. Aldehydes will end in anal. Dialdehydes will end in dial. Ketones will end in anone, and diketones will end in dione. Cyclic ketones will still end in anone, and ketenes just end in ketene. Let's name the aldehyde first. Using the main prefixes that we learned earlier in this course, a 4-carbon chain has a prefix of bute. Adding the ending for aldehydes is anal, so this is butanal. We don't have to indicate what carbon the carbonyl group lies on because it should always be on carbon 1 at the end of the chain. Now with this dialdehyde, we have a 3-carbon chain, and that is pro. When we name compounds, so the aldehydes, ketones, or cyclic ketones, that have an ending that starts with an A, we are only going to name the prefix and then connect the ending. Like with aldehydes, we had a 4-carbon chain and the prefix for 4 is bute. Then we just connected the ending of the aldehyde to get butanal. With dialdehydes, the ending is dial, and that does not start with A. So we are not going to just name the prefix. We are actually going to name the entire alkane. If we named a 3-carbon chain as an alkane, it would be propane. Then we add the ending. So we have propane dial. With ketones, again, we have an ending that starts with an A. So we have a 5-carbon chain and the prefix for 5 is pent. Because our ending starts with an A, we are only going to use pent and then connect the ending right next to it. So we have pentanone. With ketones, we do need to indicate which carbon the carbonyl is on. And this is on carbon 2, so it's a 2-pentanone. We can also name it as a pentan 2-one by putting the 2 right before the one to signify that the carbonyl group is on the carbon 2. With diketones, because the ending does not start with an A, we are going to name the entire chain instead of just the beginning, like we did with bute or pent. A 5-carbon chain, named as an alkane, is a pentane, and we just attach the dione at the end. We have pentane dione. Now we need to indicate what numbers the carbonyl groups are on. They are on carbons 2 and 4. So we have a 2, 4 dash pentane dione. We could also have put pentane 2,4 in the middle and dione at the end. Then we have cyclic ketones. These are named the same way as regular ketones, but we have to remember how to name general cyclic compounds. So to name the cyclic ketone, all we do is name the 6-membered ring and then attach anone at the end. Because our ending starts with A, we are going to do the same thing we did with ketones and aldehydes. We are only going to use the prefix instead of the entire name of the alkane. Naming the 6-membered ring would be cyclohex as a prefix. Now we add the ending instead of naming cyclohexane. We only add this ane part to the shape when our ending begins with a consonant and not a vowel. So we have cyclohex, and attaching the ending, unknown, cyclohexanone. Because the shape is in a ring, we assume that we would start counting our carbon number 1 at the carbonyl, but you can indicate 1 at the beginning of the ring or right before the own part of it, and it would still be correct. Lastly, with ketenes, I want to cover 2 different types of ketenes before we get into naming. If we have a hydrogen group coming out of this second carbon that's making up the double bond, this is called an aldoketene because the 4th group on this carbon is a hydrogen. If it was instead an alkyl group, it would be called a ketoketene. Let's try naming this aldoketene. With ketenes, we don't follow the same rules that we did for the first 5 compounds, where we have to use either the prefix or we have to use the name of the alkane. We are instead going to name the main chain as a substituent. So remember, substituents end in YL. We have a 5-carbon chain, and we should start our number 1 carbon at the carbonyl. The prefix for 5 carbons is pent, and the substituent would be pentyl. Putting that together with the ending ketene, this is pentylketene. We don't have to indicate what number this ketene group is on because we should always start counting from the number 1 carbon, and it's usually going to be at the end of the chain. However, you can put a 1 in the beginning and it would still be correct. Let's talk about the properties of some of these compounds. Starting with ketenes, the only properties I've come across are that they're usually toxic and colorless. If you know of any more, please leave them in the comments below. Now with aldehydes and ketones, most of their properties are pretty similar because they both just contain a carbonyl group within the compound. The boiling points and melting points increase with the size of the molecule, but because there are more bonds to break with a bigger shape. Take a look at this example of boiling points. The boiling point of aldehydes and ketones can be pretty similar, but it depends. If you have a ketone with 4 carbons or less, such as butanone, propanone, ethanone, or methanone, the boiling point will be higher than that of an aldehyde. In other cases where you may have more than 4 carbons, the boiling point of aldehydes seems to increase rather than the ketone. But in most classes, you won't really be asked for the difference in boiling points between an aldehyde and a ketone. It's more going to be between aldehydes, ketones versus alcohols or alkanes or functional families that are pretty different from one another. But taking a look at the boiling points of these compounds, all of these compounds have 5 carbons. However, alkanes have low intermolecular forces, they don't have any carbonyl or hydrogen bonding. Pentane will boil at 36.1 degrees Celsius. The aldehyde pentanal is going to boil at 103 degrees, and pentanone, the ketone, is going to boil at 101. The alcohol with 5 carbons, pentanol, is going to boil at 138 degrees Celsius, which is a lot more than the aldehydes or ketones because it contains the hydrogen bonding. So the boiling point of ketones is known to usually be higher than aldehydes because there are electron-donating alkyl groups on either side of the carbonyl. But if you look at the boiling point of ketones that have 4 carbons or less, they usually do have a boiling point higher than aldehydes, but with larger carbon chains of 5 carbons or more, such as pentanal versus pentanone, the boiling points of the aldehydes are actually higher. Now taking a look at solubility, both of these compounds, both aldehydes and ketones, are soluble in polar solvents like water, but usually the compounds with shorter chains are more soluble, compared to if we had longer hydrocarbon chains like these, they would not be as soluble as a shorter chain because we are increasing the nonpolar part of the compound. Longer hydrocarbon chains cause decreasing solubility in polar solvents like water. This is the same trend that we've seen with many of the other functional families, including carboxylic acids, esters, ethers, and more. So that was all for today. If this video helped you, leave a thumbs up and check out the description box for a link to the related blog post for this video. Thanks for watching.